This diagram shows the hierarchical structure of an IPv4 address. You can see how the bits group together to locate a host in progressively smaller parts of the internet, starting with the network, narrowing down to the subnet, and finally pinpointing the individual host. To figure out where those exact boundaries are, routers use a subnet mask as a mathematical stencil. Any bit that is a 1 acts like a window, letting the original IP bit filter through. Any bit that is a 0 blacks out the numbers below it, converting the host bits entirely into zeros. This table shows a clean 8-bit boundary calculation. The destination IP, 128.171.117.13, with mask 255.255.0.0, yields network address 128.171.0.0. Decimals are easy to read, but expanding this mask reveals its true 32-bit string, 16 ones followed by 16 zeros. Grouping addresses into these hierarchical ranges means a router doesn't need to memorize a path for every single computer on Earth. It only needs a single routing table row for an entire network block. That works perfectly when the mask splits cleanly at the octet dots, but network boundaries are rarely that neat. Take an IP address of 192.168.45.55 with a /26 prefix, meaning the mask ends in 192. Here, the boundary slices right through the middle of the 4th octet. To perform the mask calculation, we have to drop the decimal guessing and expand them into binary. The IP's final octet of 55 becomes 00110111, and the mask of 192 becomes 11000000. This diagram illustrates the bit-by-bit binary comparison. We apply our stencil rule again. Matching the IP address against the mask's ones drops the bits straight down. The remaining host bits are zeroed out, calculating our precise subnetwork address. While dotted decimal notation is convenient for humans, binary logic is the only source of truth when prefixes like /26 or /18 cut a network across those clean octet lines. Every subnetwork also needs a broadcast address. Instead of turning the host bits into zeros to find the network base, you flip all the host bits into ones. Let's put that into practice. Find the broadcast address for the network 130.191.0.0 with a /18 mask. Pause the video and calculate it. We have 32 total bits in an IPv4 address. Subtracting the 18 mask bits leaves exactly 14 bits for the host portion. To get the broadcast address, we flip them all to 1, modifying both the 3rd and 4th octets. Converting those back to decimal, the 3rd octet becomes 63 and the 4th becomes 255. The correct broadcast address is 130.191.63.255. The broadcast address acts as a loud shout to every device on that specific subnetwork. Pinpointing exactly where the mask ends and the host bits begin is the only way to direct that shout correctly. Let's build on this by creating our own subnets from scratch. Suppose we need to divide the network 192.128.0.0/9 into 4 equal subnets. To get 4 distinct networks, we need 2 to the power of 2. So we borrow 2 bits from the host portion, pushing our mask from a /9 to a /11. Those 2 borrowed bits give us 4 binary combinations, 00, 01, 10, and 11. When we cycle through these in the 2nd octet, our subnet addresses increment in chunks of 32. We get 128, 160, 192, and 224. If we have a specific host address, like 192.192.4.7, we can check which network it belongs to. By looking at its 2nd octet, 192, we can see it matches up perfectly with our 3rd subnet block. Here are the core rules to remember. Ones in the mask define the network and subnet. For the host bits, all zeros gives you the subnet ID, and all ones gives you the broadcast address. Stepping out of decimal and calculating in binary removes the mystery from messy prefixes. It allows network administrators to take any block of addresses and divide it with strict mathematical precision.